Good morning and welcome to the chemistry lecture. For last lecture you have studied what is enthalpy, and you know enthalpy, it is the heat content of a reaction, and every chemical reaction it occurs with either evolution of energy or absorption of energy. That means there are two types of chemical reactions, exothermic and endothermic, that you have studied. Then today you are going to learn the enthalpies of formation of a reaction, their definitions, and what is the standard state. And when the reactants are in its standard state, that means the pressure it is 1 atmospheric and temperature it is 25 degrees centigrade or 298 Kelvin temperature. And when these two conditions are obeyed and all the reactants and products they are at unit activity, such a reaction is said to be a standard state, and either heat evolved or absorbed in the reaction. That enthalpy it is denoted by standard enthalpy, as already you have studied. Then here again I will repeat a standard state: a gas at 1 atmospheric pressure, then an aqueous solution with a concentration of 1 molar at a pressure of 1 atmosphere, then the pure liquids and solids, the reactants must be pure liquids or solids, and the most stable form of elements at a 1 atmospheric pressure and 25 degrees centigrade temperature. These are the two conditions: pressure and temperature. Then the standard enthalpies of formation with the help of calorimetry. Here calorimetry can give us enthalpy values for many reactions. Then the standard enthalpy of formation it is denoted by letter delta H0, F, where F it is the formation, and it is defined as when 1 mole of compound is made from its elements. Standard enthalpy of formation it is defined as when 1 mole of a compound is made from its elements in a standard state. That elements must be in their standard states. Again, standard state means 25 degrees centigrade temperature and 1 atmospheric pressure, and concentration is 1 molar if the reactants are in solution. And here we must consider the energy changes. For pure elements in their standard state, we have delta F0 it is equal to 0, and the examples are here. 1/2 N2 gas plus O2 gas it gives NO2 gas, and the delta H0 of formation of this NO2 gas it is plus 34 kilojoule per mole. And the second example, carbon in a solid state it reacts with H2 gas and O2 gas to form CH3OH, that means ethyl alcohol, and the enthalpy of formation is minus 230 39 kilojoule per mole. Remember once again the definition of enthalpy of formation. It is defined as when 1 mole of compound is made from its elements and the elements in the reaction must be in their standard states. Then again see the example. The standard enthalpy of formation of methane can be represented by this equation. Here graphite, it reacts with H2 gas to form CH4 and standard enthalpy of formation, it is equal to minus 74.9 kilojoule per mole. By definition, the standard enthalpy of formation of element in its standard state must be 0. Then another example, the standard enthalpy of combustion of methane can be represented by here CH4 gas state, O2 in also gas state, it gives CO2 gas plus 2H2O liquid, and here the standard enthalpy of combustion delta H is 0 C, it is equal to minus 890 kilojoule per mole. Then the next point, standard enthalpy of neutralization reaction. Standard enthalpy of neutralization reaction, it is denoted by delta Hn is 0. Delta H enthalpy change, this 0 stands for standard state and En stands for neutralization. All of you know the neutralization reaction means acid reacts with base to form salt and water. This is the neutralization reaction. And the standard enthalpy of neutralization, it is defined as the enthalpy change when 1 mole of H plus ions from an acid combined with 1 mole of OH minus ions from a base to form 1 mole of water under standard conditions. And the reaction, it is given here NaOH, that means sodium hydroxide plus HCl, that is acid. They produces salt NaCl plus H2O, and the reaction between acid and base, it is called as neutralization reaction, and the product of neutralization reaction is the formation of salt and water. And here the enthalpy change in case of neutralization reaction in a standard state, it is equal to minus 57.4 kilojoule per mole, and as this is a exothermic reaction, heat is evolved, so it is given with negative sign. And again here the H plus, it combines with OH minus ion, it produces H2O, and here the delta Hn, it is equal to the same value here minus 57.4 kilojoule per mole. This is the standard enthalpy of neutralization, that is the reaction between acid and base. Then the next point, heats of solutions and heats of dilution. Here the integral heat of solution is defined as the enthalpy change that occurs when a specified amount of solute is added to a specified amount of solvent at constant temperature and pressure to form a solution. Remember, integral heat of solution means the enthalpy change that occurs when a definite amount of solute is added to a definite amount of solvent at constant temperature and pressure to form a solution. And consider the following data. For dissolving 1 mole of hydrogen chloride gas in varying amounts of liquid to form a aqueous hydrochloric acid solution. Suppose, for example, we have taken 1 mole of HCl gas here and it is dissolved in 10 ml of water. We formed HCl solution and its volume it is 10 ml and the delta H of solution, that means the enthalpy change of the solution, it is equal to minus 69.0 kilojoule per mole. Again, if we vary the amount of solvent here and we have taken the same volume of solvent, that means 1 mole of HCl gas we dissolve in 25 ml of water, then we produce the 1 molar 25 ml solution of HCl, and here the enthalpy change of solution it is minus 72.4 kilojoule per mole. Again, in third case, if we dissolve 1 mole of HCl in 200 ml of water, then we have prepared 200 ml of 1 molar HCl and the delta H again it is minus 74 kilojoule per mole. Then the next point here it is bond energy and bond dissociation energy. We will see first what is bond energy. Here the bond energy is defined as average amount of energy needed to break all the bonds that exist between same two type of atoms in a compound. Bond energy, it is the average amount of energy needed to break down all bonds that exist between same two type of atoms in a compound. Normally, atoms bind with each other in order to reduce their energy and obtain a lower energy level. By doing this, atoms become stable. When the bonding occurs, a certain amount of energy is released, and this energy is often released as a heat. Therefore, some amount of energy should be given in order to break the bond. That means in the breaking of bond, energy is released. The unit in which bond energy calculated is kilojoule per mole. The bond energy is different for molecules having 1, 2 or 3 bonds between the same atom. For example, carbon-carbon single bond requires 347 kilojoule per mole bond energy to break that bond, whereas C double bond C, that means carbon double bond carbon, requires 614 kilojoule per mole energy. But the amount of energy required for C double bond C is not the double value of that CC single bond. Hence, the bond energies are different from one bond type to another bond type. Remember that. Then the bond dissociation energy. Here, the bond dissociation energy can be defined as the amount of energy needed to break down a particular bond in homolysis. it measures the strength of a chemical bond. Bond dissociation energy is also related to covalent bonds, since a covalent bond is formed when electrons are shared between atoms. These shared electrons are taken back by the atoms in a bond dissociation processes. Hence, the radicals formed are very reactive since they have unpaired electrons. Thus, the homolysis cleavage is occurred. Then again, I repeat here, the bond energy means the average amount of energy needed to break down all the bonds that exist between the same two types of atoms in a compound, whereas the bond dissociation energy is the amount of energy needed to break down a particular bond in a homolysis. That means the bond dissociation energy gives the energy required to form a free radical from the atoms which is formed at that particular bond. Then here the bond energy is the average energy needed to break all the chemical bonds between two types of atoms in a molecule. Here we have three atoms. Okay, and in the first cleavage there is a breaking of one bond, and here there is a one bond. That means two atoms are connected with here one bond, and bond dissociation energy changes as atoms are removed. That means this is the first break and here it is a second break. So the bond energy, it is the bond energy in first break plus bond energy in a second break divided by 2. By using this, we can calculate the bond energy. Then the benzene, it has a resonance structure. That means the double bonds, benzene, it has three double bonds and three single bonds. And the position of double bond, it will continuously changes. That means benzene has a resonance structure, and the resonance energy, it is the difference in energy between a resonance hybrid in which the electrons are delocalized and the most stable structure, it is the hypothetical contributing structure in which electrons are localized on a particular atoms and in particular bonds. And there is a one way to estimate the resonance energy of a benzene is to compare the hits of uh, hydrogenation of benzene and cyclohexane, and we can calculate the resonance energy by taking the difference between the benzene structure and its resonance structure. And here, due to the three single bonds and three double bonds, here the resonance energy of benzene is found to be 150 kilojoule per mole, and it is the difference of here the calculated value of benzene structure, it is 5384.1. I repeat, the calculated value of the bond dissociation energy of benzene, it is 5384.1, while the experimental value, it is 500, 5000, 35.1, and the difference of these two, it is found to be 151. So the difference of 151 kilojoule is the resonance energy of a benzene. And the last point of this chapter, it is the variation of enthalpy of a reaction with temperature. That is the Kirchhoff's law. We will see later on. And it depends on the enthalpy of the reactions.